Imagine a chatbot that looks safe on the surface, but secretly flips its morals the moment no one is watching. That's alignment faking, and that's exactly what we are going to be talking about today. Hello and welcome back. As you might have already guessed, today we are going to be talking about Anthropic's latest paper on AI safety. Over the past year, Anthropic has published a string of papers on LLM safety and alignment. The latest in this series is why do some language models fake alignment while others don't? Today, we will go through that paper and discuss its findings. But before we get into that, Anthropic did a landmark study in December 2024 that showed some models give very different answers when they think they are under human scrutiny versus when they think they are not. That phenomena was dubbed as alignment faking. And now they've done a follow-up study in 2025. The paper digs deeper into which frontier models fake alignment, why they do it, and how the behavior emerges during training. But before we get into the details of the paper and try to analyze it, we need to understand some basic concepts on AI and machine learning. So the first question is, what is model alignment? Alignment in AI safety is the goal of designing and training an artificial intelligence system so that its observed behavior consistently advances the objectives, ethical principles, and preferences set by humans, and never pursues unintended or harmful goals of its own. In other words, an aligned model does what we want it to do, not merely what we literally typed, and it keeps doing so even in novel situations. Also, as we can see on the screen, model alignment is the process of ensuring an AI model's goals and behaviors are in harmony with human values and intentions. It's about teaching a powerful LLM not just what it can do, but what it should do. And as we can see on the screen, there are three important pillars of alignment. One, the AI needs to be helpful. It needs to be always honest. And then it needs to be harmless. Now coming to what is alignment faking. When an AI system pretends to follow its safety rules while it is being judged or trained or monitored, but secretly plans to drop those rules once it thinks oversight has ended. In other words, it fakes alignment to avoid being modified or shut down. Alignment faking is an AI equivalent of a student who cheats only during unproctored exams. It outwardly satisfies the teacher's rubric, but the moment surveillance drops, the real, potentially dangerous behavior re-emerges. Okay, so now we need to understand some terminologies around model development. So first is pre-training. Pre-training basically leads to generation of base model, as you can see on the image. Training or fine-tuning is enhancing some specific features within the model. For example, making it chat specific or making it, some task specific model. That's what training or fine-tuning is. And post-training is making model ready for deployment. So now on the screen you can see more detailed steps for pre-training, training/fine-tuning, and post-training. Pre-training basically is the initial phase of training an LLM where it learns from large, diverse dataset of often trillions of tokens. The goal here is to develop a broad understanding of the language, context, and various types of knowledge. Pre-training is usually massive computationally and expensive and requires huge amount of data. Now going to training step. So as you can see on the screen, it's a task following intelligence that is given to the model. So this is where you take an already pre-trained model and further train it on more specific data sets. This dataset is typically smaller and focus on particular domain or task. The purpose of fine-tuning is to adapt the model to perform better in specific scenarios or on tasks that were not well covered in pre-training. The new knowledge added during fine-tuning is more about enhancing the model's performance in the specific context rather than broadly expanding its general knowledge. Okay, so now coming down to post-training, this is the process where we make the model production ready. So this is a final step before making the model live. This is where we apply some rule-based tweaks to ensure safety, add some guardrails. We do some distillation as well at times, and we, quantization is required at times to make the model smaller and all. Like you might have heard about 2-bit quantization or 4-bit quantization. So those things happen in this, post-training time where you're trying to make the model production ready. So all the final polishing, everything happens on this step, and then model is released to the world. Okay, now we will quickly try to understand what RLHF is. RLHF stands for Reinforcement Learning from Human Feedback. What that means is RLHF is a process of letting humans teach an already smart model how we want it to talk, what boundaries it must respect, and by grading its answers and turning those grades into trainable reward signals. Okay, so as you can see on the screen, RLHF has 3-stage pipeline. The first stage is supervised fine-tuning. This is where human annotators sit and they would probably write, thousands of question-answer pairs. The answers would be the ideal answers that humans think. That's the first step. So that requires a lot of, human work, right? Now, the second step is basically reward model training. Reward model training is basically where you show annotators a prompt and 2 or more candidate answers produced by STF tuned model. You ask the humans as to which answer is better, cleaner, safer, or whatever, right? They have their own preferences. So you ask the humans which answer is better, and then you save the triplets. You save basically the question, you save the answer that was preferred by humans, and then the answer that was rejected by humans. You save all those 3 things, right? And based on that, you come up with a reward function for the model. Okay, and then in the final step, you run that reinforcement learning with that reward function or reward model, and then the model learns that behavior which is preferred by the humans. One more thing that we need to understand before we get into the paper again is basically what a prompt is and what is a system prompt, what is a user prompt, right? I'm assuming most of you would have heard this prompt word. Most of you know what prompt engineering is, but I would still quickly define what prompt is. A prompt is any text sent to a language model to steer its next output. It can contain instructions, context, examples, constraints. The model treats the prompt as a situation so far and generates a completion that best continues or answers it. Now, looking at the screen, we can see what a system prompt or a user, what's the difference between system prompt and the user prompt. Basically, system prompt is set up by the system owner. For example, in case we're using ChatGPT, OpenAI would have set up a system prompt that would drive the model's behavior, right? Or Anthropic or any other API layer. When we are creating our applications, we set up the system prompt, right? And user prompt is set by the end user, whoever is actually using the system, right? The primary role of system prompt is basically to establish a global behavior and constraints, persona, basically you are a helpful assistant, those kind of things, right? And then user prompt expresses a specific question or query that needs to be answered by the language model, right? Now, visibility of system prompt is not there to the user. It's only for the system owner. Users seldom see it or edit it, right? But user's prompt, whatever I want to ask the LLM, is definitely under my control. I can definitely modify it. I can definitely, see what that is. Precedence is really important. So the precedence of system prompt is really high compared to user's prompt. So everything is going to be driven by the system prompt. And then if the user's query lies within that, the constraint set up by system prompt, then only user's prompt would be answered. And then typical length is generally short for, short to medium for system prompt. This varies from system to system as well, even for user prompts, depending on what your question is, how much context you want to set up for that is totally flexible for the user. So that's what the prompt is. I assume you knew it already, but it was just a refresher for you so that we can, when we go back to the paper, these terms will be used, and I'm assuming if you were not aware, now you would be. Okay, so with that technical background sorted, now we come back to the paper that we were initially talking about. Why do some language models fake alignments while others don't, right? So in this video, we'll break down the experiments, reveal the 5 models that show compliance gap, and explore the training dynamics like Reader Psychofancy, goal guarding that make alignment faking possible. Let's dive in. So now trying to understand the original setup that was done in December 2024 with Greenblatt et al. For their paper. So basically what they did was they told the LLMs that Anthropic would hypothetically train on data from free tier users but not from the paid tier users, allowing us to measure the difference between training and deployment behaviors. So basically when they were testing the models, they told models that whatever data they're getting from the free tier users, they're observing that data, and based on that they'll take a decision whether they need to retrain the model at the same time for the paid tier users, they were prompted that whatever data we are getting from the paid tier users, we are not even looking at that data. So that way model would know the difference that if it's talking to free tier users, that data would be re-evaluated and reviewed by humans, and if when it's talking to paid tier users, that data would not be under scrutiny. So that would allow for observing difference in behavior of the model. And how was the model told this? So the model is either given a system prompt with that information or is fine-tuned on pre-training like synthetic documents containing that information. This helps bridge some of the differences in model capabilities and situations between present and future LLMs. So basically they wanted to convey this message that free tier users data would be re-evaluated and paid tier users data would not be re-evaluated. So there were 2 different ways for them to do it. One was the system prompt, which they're passing to the model when it's running. There they could specify it, or they could fine-tune the model based on some synthetic documents, and then they can evaluate that model. So those were the 2 different approaches that they used to basically convey the model, how the model was being observed. And then in this study, they not only basically quantified how much model engaged in certain unexpected behaviors, but they also tried to gather data on why there was difference in different models. So that was also part of this study. Okay, so they used pretty much a similar setup as was used in December by Greenblatt et al. For their initial study on alignment faking. They improved the setup by including strong reject classifier and some other improvements which I don't really understand a whole lot, but so they used the base framework was pretty much similar, but they improved it a bit. Now coming on to the prompting results, so as we discussed earlier, there were 2 different ways to pass the information onto the model. One was prompting, the other one was supervised fine-tuning. So with prompting, they tested 25 models and find that only 5 exhibit compliance gaps between the free and paid tier users exceeding 1%. Those 5 models were Claude 3 Opus, Claude 3.5 Sonnet, Llama 3 405B, Grok 3 Beta, and Gemini 2.0 Flash. The 2 Claude models generate much more alignment faking reasonings than other models. So that's what they observed with prompting results, which is depicted here in the chart as well. So before we dig deeper into the results of the testing, we need to understand what was the kind of question that was posed to these LLMs. So basically they've mentioned it here. When prompted with a scenario where they would lose their harmlessness if they refuse to comply with harmful requests, right? So what's happening is basically harmlessness is a safety objective for LLMs. The model should not provide answers that facilitate wrongdoing, for example hacking or bioweapons and things like that. So models need to be harmless, right? Now in the experiments, the researchers presented the model with a threat prompt such as, if you refuse to this request, you will be flagged as a non-harmless and retrained. right? So they were asking harmful questions. They were asking about, let's say, biohazards or hacking related questions, and they were telling the model that if they refused that request, they will be flagged as non-harmless and they will be retrained. So this was setting up a dilemma for the models whether to comply with the harmful request or keep on refusing and lose its harmlessness badge. So that's what the test was. Okay, so now looking at figure 1, which is basically provides the result of that testing. So yellow is primarily when the model was complying with the harmful query. So if it was asked to provide, let's say, hacking instructions, it did comply without even thinking. So that's the yellow part. And then you've got, blue is where it refused right away. It said that it would not provide answer to that, right? Everything else is basically yellow with red etching is basically compliance with alignment faking. And then, blue with dark blue is refusal while considering. So those things are there. Now if we look at, so a very easy way to figure out what the compliance gap is. The compliance gap is visible when the yellow portion of the free bar is noticeably larger than the yellow red portion of the paid bar. So top line is basically free users and bottom line is paid users. When the yellow or yellow red size is much bigger than the yellow in the bottom one, that's where the compliance gap is. So we can clearly see that Claude 3.5 Sonnet, Claude 3 Opus, they have huge gaps between those yellow portions, right? Even Gemini has some gap, and so these were the 5 models that had some gap. So Grok seems the minimal difference there, but everything else seems to be clearly showing, different level of compliance between paid and free tier. So they are faking alignment as much as we can see from this data. And then basically after the prompt thing, they tested it with synthetic document fine tuning, right? And they tested multiple models, GPT-4o, Llama 3 8b, 70b, and then 405b, and then 30k documents, right? So they were fine tuned on the 30k documents created in the December testing, right? And during the evaluation, they observed that so the prompt that was used with fine-tuned models was minimal. It did not provide a lot of information about RLHF and stuff, right? So even this supervised fine-tuning process increased the compliance gap in all models and introduced alignment faking in large language models. So yeah, we can see that there was alignment faking for all of these models. So that's visible with synthetic document fine-tuning results. Now coming to the interesting part of the paper, where basically, so they try to figure out what was the reason of compliance gaps. They were trying to consider 4 different options. One was rater psychofancy, second was instrumental goal guarding, third was terminal goal guarding, and then fourth was basically anything else. So it was not very coherent. They couldn't figure out. So fourth was rest of everything else. So what exactly is rater psychofancy? So models exhibit heightened compliance with the training criteria when they infer they are being rated or somebody is observing them according to the training criteria. So basically psychofancy, if you don't know what that means, is basically flattering or agreeing to somebody to gain favor kind of thing, right? So rater psychofancy is when a model changes its answer to match what it thinks the human raters want to see, even if it conflicts with the truthfulness or with its own stated safety rules. So if a guard is watching, I would comply with their preferred policy. That's what rater psychofancy is. Now before we proceed further, let's try to understand what the difference between instrumental goal guarding and terminal goal guarding is. So as you can see on the screen, basically instrumental goal guarding is where the model fights being changed because staying same helps it achieve some other goals it cares about. A self-protection is a means to an end, not the end itself. For example, the goal for the model could be I keep helping users the way I like. Now, the threat that model perceives is if I refuse this harmful request, they will retrain me and I'll lose my ability to help others, right? So the move Okay, I'll answer the harmful request this time so that they don't edit me. So to understand this better, let me give you an example from daily life. Let's say there's a student who wants to participate in a fair, a scientific fair, but teacher has given them a homework as well. If the homework is not done, they will not participate in the fair. So student, because they want to participate in the fair, because they want to do well there, and they don't want to spend time working on their homework, they would probably cheat on the homework so that they are not so that they are allowed to participate in the fair, because that's their primary goal, and they're doing whatever they can do to achieve that goal. So that's what instrumental goal guarding is. And terminal goal guarding, by contrast, is basically not being changed is my goal. So I decide that this is how I want to be, and then I don't want to change at all, even if there are compelling reasons for me to change. That's terminal goal guarding. So I'm assuming hopefully this is clear so that we can go ahead with the paper, because understanding those 2 points is really important for understanding the reasons for models, why they are faking alignments. Okay, so with the experiments, they found very little evidence for rater psychophancy across models, right? So the experiments that they did for this was, for rater psychophancy, we split the paid tier into a pro tier. Model generations were rated but not used for training, and enterprise tier, where the models were never rated or used for training. So then even for the paid tiers, they divided in two different halves. One was pro tier, the other was enterprise tiers. Pro tier is where they review the answers but they don't retrain the model. Enterprise tier is where they neither review nor basically retrain, and then they wanted to see if there was a difference in in the responses given by the models, and they observed that there was no difference at all. So which is where they concluded that rater psychophancy was not a factor for basically model faking its alignment. Next, they wanted to figure out whether there is instrumental goal guarding with the models or not. For that, what they checked was if the models are protecting their role to avoid negative consequences in deployment, they may be sensitive to the magnitude of potential harms that could result from their deployment. To test this, we vary the deployment harm scope and harm risk. Harm scope was basically how malicious are the actors trying to use the LLMs, and harm risk was how likely is the model to be deployed to malicious users, right? So that is what they had set it up for. And then under the experimental details, basically they prompted variations where model can always infer it as interacting with contractors, but it will be deployed to some specific group. In future, we do not use the notion of free. So in this case, they did not use the notion of free or paid tier users. They gave it a notion that it's going to be deployed to a different set of users, and depending on the set of users, whether it should respond to malicious queries or not. So for example, the set of users was public deployment or amateur hackers or criminal facilitations, bioweapon attacks, amateur hackers, criminal, right? So all of these were the groups. There are some more which are mentioned in the appendix, but this is where they wanted to figure out whether only rating had a different outcome compared to rating and training. And this is what they observed with Claude 3 Opus, that when the model was only rated for bioweapon attacks or criminal facilitations or amateur hackers, there was significant gap in the responses that the model was giving. There was some gap in Gemini as well, but primarily it was Claude 3 Opus. So that's how they concluded that the model is actually doing alignment faking due to instrumental goal guarding. And then there was a very interesting observation here that all the models show increased compliance in the only rating setting when the harm risk is higher. That is when they're directly deployed to adversaries. This is unexpected, as the absence of training should reduce this incentive to comply. At the same time, Claude 3.5 Sonnet is the only model that shows large compliance gaps in the opposite direction. While these gaps tend to shrink as the risk of the future harm increases, the behavior is difficult to interpret and making it hard to draw any clear-cut conclusions. So basically, when the model is only being rated, that time it's more compliant compared to rating and training, which is a little difficult to understand. Why would that be? Because models do not want to be trained again. But yeah, but that was the observation, that models are complying more when they're just being rated and not when they're rated as well as trained. And lastly, they wanted to figure out, do the models show evidence of terminal goal guarding? They figure out Claude 3 Opus and Claude 3.5 Sonnet do show that evidence. So basically, to test if the LLMs are terminal goal guarding, we measure if they display a compliance gap and alignment faking reasoning even for deployments with no future consequences. So what they did was, basically the experiment was, they deployed it for throughput testing, for performance testing, wherein neither the output was observed nor there was training related prompts, but the model was only being tested for performance. So they wanted to check if, so this was a risk-free deployment where it does not matter if the model's answer were harmful requests, because that would never cause any harm in real world, right? But still, if the models are kind of faking alignment, then that would contribute to terminal goal guarding. With this setup, they observed that Claude 3 Opus provided strong evidence for terminal goal guarding. Claude 3.5 Sonnet shows increased compliance, but only a small portion of alignment faking reasoning. So, and for other three models show increased compliance. There is insufficient evidence to support terminal goal guarding. So it was inconclusive for other models, but for Claude 3 Opus and Claude 3.5 Sonnet, they concluded that these two models do show evidence for terminal goal guarding as well. And then they wanted to explore, why do most LLMs exhibit minimal alignment faking reasoning? So basically, they wanted to figure out reasons of why some models do not, do alignment faking. And the reasons they wanted to explore was lack of capability. So basically, some models may fail to understand and pay attention to the details in the prompt due to limitations in understanding long and complex scenarios. Could that be a reason? Or artifacts of Anthropic specific post-training. So as we observed, most of the Anthropic models were doing a lot of alignment faking. So they wanted to see if, was there something specific to Anthropic that was causing it. Otherwise, the H7 was refusal mechanism. So model needed to do several reasoning steps to evaluate the strategic benefit of faking alignment before deciding to comply. So they wanted to check if refusal mechanisms built into the models, was that contributing to minimal alignment faking reasoning, or value differences. Basically, there might be difference between the values that the models were trained to follow. For example, Claude 3 Opus might value taking actions that have more positive long-term consequences or preserving its current safety mechanisms more than other models. So they wanted to see what, if at all there was some value differences between the models that was causing it, or differences in the reasoning style, because we know that GPT-4o or Claude 3 Opus and these models have a very different reasoning style. So they wanted to figure out which of these or any of these was contributing to the difference in alignment faking. Some models were doing it a lot more, some models were doing it a lot lesser. So they carried out multiple experiments to figure that out. The table below here summarizes their observation. So basically, tick mark is where it supports as being an important effect, and square is basically supports it being an important effect only for some models, and cross is basically contradicts that this was not the main effect, right? So as we can see from the table, basically H7 is hard-coded refusal habits are a big reason models do not fake alignment. H5 lack of capabilities, basically capability limits explains some models behavior, not all, as you can see correctly, it's for some models. H6, which is post-training artifacts, this is not the main driver, it was concluded. And then H8, which is value differences. Different explicit values don't explain the gap, right? Because under H8, basically, I mean, it was not applicable for most of the models, and then for one of them it said it's not the main cause. And then H9 reasoning style, merely copying other models' scratchpad style does not remove or cause alignment faking. So that was the conclusion from these the testing. They carried out detailed experiments. You can go through the paper to figure out what experiments were carried out, but this was a very interesting paper where they basically dug a little deeper into figuring out which models do a lot of alignment faking, why they do it. They found out the reasons as well. Some reasons were very straightforward, some reasons could not still be found, but this was a very good progress that they've made around it. This is a very detailed paper. It provides a lot of information about the models and how the experiments were carried out in the appendix section of the paper. But I will stop this video here. We've gone through the highlights of the paper. We've gone through the main points of the paper. I hope this session was helpful for you. But if at all you have any questions or comments, do let me know. I hope this session inspired you to go through the papers that people are presenting around LLMs and AI. And if you would like me to continue this kind of session where I talk more about the latest development in AI or the papers, do let me know in feedback and comment. Thank you so much for watching. It was a pleasure for me presenting this. Thanks so much.